Unraveling the composition of Earth's core, a deep dive into the inner core's formation. Imagine a world where the very core of our planet, the Earth, holds secrets that could revolutionize our understanding of its evolution. This is the captivating story we're about to uncover, focusing on the enigmatic inner core and its role in shaping the composition of Earth's core. The core's composition, a crucial puzzle piece. The composition of Earth's iron-rich core is a key factor in understanding the dynamics and evolution of our planet's deep interior. It sets the temperature at the inner core boundary, influencing the present-day temperature at the core mantle boundary. This temperature, in turn, affects the core's transport properties, including thermal conductivity, which is vital for determining the long-term thermal evolution of the core and its ability to generate the global magnetic field. Light elements. The missing link. Light elements, such as silicon, sulfur, carbon, and oxygen, play a significant role in the growth of the inner core. They determine the strength of compositional buoyancy, and their partitioning between solid and liquid during inner core freezing is crucial. Chemical exchange at the core mantle boundary may also create stable regions at the top of the core, detectable through seismology. A compositional mystery. Despite recent advancements, the composition of Earth's core remains largely unknown. Three main approaches have been used to constrain this composition: cosmochemistry, core formation, and seismology. Each approach provides insights, but no single composition can fully explain the origins, formation, and elastic properties of the Earth's core. This has led scientists to seek additional constraints that are independent yet complementary to existing methods. The inner core's nucleation, a powerful constraint. The classical understanding of the inner core's formation suggests that it occurred when the temperature of the core at the Earth's center cooled to its melting temperature. However, this picture is incomplete. All liquids must be supercooled below their melting temperature before freezing can begin. This supercooling requirement varies with composition, and not all potential compositions can explain the presence of the inner core. Carbon, a key player. In this study, researchers have extended their previous work on the FEC system, which showed that elevated carbon concentrations significantly reduce the supercooling requirement for nucleation. This finding narrows the gap between the supercooling needed for inner core nucleation and the supercooling compatible with observations of the deep Earth. The results suggest that a carbon concentration of 0.1 could allow for homogeneous nucleation of solids at the center of the completely liquid core. Heterogeneous nucleation, an alternate path? Heterogeneous nucleation offers an alternative route to inner core formation, but it requires the presence of a pre-existing solid surface as a nucleation site. While this process still requires supercooling, it can reduce the free energy barrier compared to homogeneous nucleation. However, finding a solid phase that can avoid dissolution and melting in liquid iron remains a challenge, and no known material currently meets these requirements. Implications for core composition. The composition of Earth's core is likely more complex than simple binary alloys. However, the simplified FEC compositions discussed here provide a useful context for understanding the available constraints. Geophysical constraints, such as radially varying core density and seismic wave speeds, can be explained by the presence of light elements, like carbon and oxygen. Matching the core mass and density jump at the inner core boundary requires at least one other light element that partitions more evenly between the inner and outer core, such as sulfur, silicon, or hydrogen. Future research directions. Studying nucleation in binary alloys is already challenging, and no studies of ternary alloys have been attempted yet. The effect of hydrogen on the melting point may suggest even longer waiting times than found in the FEC system. Other light elements have been shown to stabilize phases of iron, but this effect has not been observed in binary systems so far. Ultimately, while many candidate compositions can reproduce available constraints, only an FEC composition has been shown to explain the nucleation of the inner core, while satisfying seismological requirements for light elements. A conclusion. The process of inner core nucleation can provide a strong constraint on core composition, especially when combined with thermal evolution modeling. It is essential to reconsider previous inferences of core composition in light of this additional constraint. Future research should explore core compositions featuring carbon and nickel, as these elements may trigger inner core nucleation at geophysically compatible supercooling while satisfying seismological requirements. References. List of references as provided in the original text.